let's get started. So every time you should look at the updated lecture note, hopefully. So yeah, every time I will update the lecture note. So yeah, just go to overlays to see the latest lecture note. Otherwise, the some information may be not updated. The previous lecture note. Last time we talked about the classical field theory, and then so we talk about Lagrangian formulation, Hamilton formulation, and then we introduce the so-called the Nathan theorem. So if there's a symmetry, there's a concept current, and then we find the stress energy momentum tensor. Energy momentum tensor, and then so we reach here, and as I mentioned, this is usually in general it's not symmetric, and to make it symmetric, you have to introduce there's some suitable tensor such that the P mu like this way. So to make it, I just didn't make a remark that the this tensor should obey the following quantity property. So if you swap nu and rho, it should be antisymmetric. For this reason, because we need a conservation of current, stress energy tensor, energy momentum tensor. And if you apply it, this one is the T mu nu. This is automatically so this is the case, and if this rho and mu under exchange, if it is antisymmetric, this is automatically 0. Okay. So therefore, this is 0. So therefore, this is 0. So we already knew that this one is concept quantity. Okay. So that's the case. And I also give the example that this is not a symmetric case. So for instance, if you start with Maxwell Lagrangian minus 4 F mu nu F mu nu. And this F mu nu is the F mu nu. So this is the case, and if you take the following, the T mu nu is indeed so maybe I should write down like this way. Then this part is indeed equal to minus mu rho. I think maybe I should write down like this, maybe mu rho, mu a rho. So therefore, under the exchange of mu and nu, it's not symmetric this time. This term is not symmetric. But if you add s, so in this example, so is it okay? In this example, if you set s, sorry, it was raining and I just kind of came by bike, so my back is not, it's dirty. Sorry. S lambda mu nu x mu lambda and nu. So if you introduce this one, what you get is that the desired form of the stress energy tensor. So this is the desired form of the stress energy tensor. Okay. And if you use the original, the intrinsic definition of the intrinsic definition of the stress energy tensor. This is T mu nu, then this is exactly equal to this. You can check by yourself. It's a good exercise to do that. Okay, this is the part I think I missed some explanation at the end of the lecture. Any question? Okay, so this is a review of classical field theory, and I'm going to. Is it annoying? So, I think it, yeah, it should be fun. So, and then now we are going to quantize classical field theory in scalar Lagrangian. Scalar field theory. Okay, so the goal, next goal is quantize. Next goal. Quantize free scalar theory. Lagrangian is given by this one. 1/2. Sorry. I think I need to be careful. Minus. I forgot already. Minus. No. So this is I'm going to quantize. Oh. Yeah, please be careful. If you sit in front. Okay, so that's what we are going to do. Hopefully I'm not mistaken. Okay, good. Oh, sorry, I go for 1/2. 1/2 here. Okay, so that's Lagrangian for free scale theory. So we want to quantize free scale theory. But before that, let's review by canonical quantization. By canonical quantization. Before that, let's review some basic of quantum mechanics. The harmonic oscillator. So a harmonic oscillator is essentially quantization, canonical quantization, free scalar theory is just some huge generalization of the harmonic oscillator. You just get this creation annihilation operator to infinite many creation annihilation operator for free scalar theory. So the review of harmonic oscillator is very eliminating. So Hamiltonian is given by, as you know, 1/2 E square plus 1/2 omega square Q square. And we apply the canonical quantization condition. It's just P and Q are this relation. So this is the canonical quantization condition I told you last time. And then, so we introduce to quantize this Hamiltonian, we introduce this canonical quantization. So therefore, P is essentially equal to by Q. Maybe I, whatever I, maybe plus minus. P is equal to plus minus, something like this. And then this relation will be satisfied. will be satisfied. Let me think. It should be, yeah, plus. It should be plus. Then, so to see the spectrum of the harmonic oscillator, we introduce the, as we know, already very familiar thing, Q plus I square root to omega P, and the A dagger, is equal to so then, as you know, so you introduce this one, the Hamiltonian can be written as the something like this one. 1/2 omega A dagger plus A dagger A. So that's our familiar stuff. We know. I mean, essentially this is equal to 1/2 P square and Q square. Omega is just you can set 1 if you, or make it simple if you want. But then everything clear. And this canonical quantization will impose this kind of condition. So if you consider now, so we treat Q and P as operators. Okay, P and Q are operators. So therefore, so A is now operator. Okay. So therefore, you can consider the computational ratio operator, and essentially what we want to see is essentially minus I over 2. So Q itself commute, P itself commute. So what's important is diagonal form, diagonal commutation. Therefore, if you look at the commutation ratio, this one, square root omega cancel, and you get to minus I over 2 as I over 2 and the QP. And the next is the this one and this one. So therefore, so this is plus I over 2 and the PQ. And of course, if you swap the order, what you get is the I over Q and P, and this is equal to 1. And if you plug that one into here, you get the 1. Do you understand? So it's very familiar stuff. You should know. And then, so Hamiltonian is this guy. But you have to be a bit careful about the ordering. So now order matters. A dagger or A dagger A is a bit different because of this computational relation. And then, so if you swap this order, you get the extra 1 term. So therefore, this you get the A dagger plus 1/2. And usually people just call this A dagger A is numbering operator. You can define as the omega is numbering operator 1/2. That's familiar stuff. And then, so there's the extra constant here, so therefore ground state energy is something like a ground state is something like a different. You just define the ground state as the something like a A0 is equal to 0. So this is the ground state. So therefore, A annihilates, so what's left is this one, and this 1/2 is 0 point ground state energy. That's very familiar stuff. You must be familiar with. And then, so this is the ground state and excited states. So what we need is that we just keep acting. So this is ground state. This is ground state in the excited state. Is you just keep adding up to some normalization. Usually, okay, if you're very careful, you need to add this kind of term, A dagger, so this A dagger is a creation operator, and if you add the n times, you get the, and then so, I mean, so this is energy, and this is the Q. And the potential something like this one, direct potential, and then you have ground state is something here, 1/2 omega, and then 3 halves, and 5 halves. Sorry, my drawing is not so good. Is there any color chalk? Yeah, great. Then the wave function is the for ground state is something like this one. I mean, and then this is 0, and this corresponds to 1, and then I need to be careful about the drawing, like this. Oops, sorry. Is 2 and so on, and so this is the wave function of the harmonic oscillator, and so on. Then numbering operator, the Hamiltonian acting on the excited state is just omega n, small n plus 1/2 z. So this is the energy eigenvalue for excited states, and then we sometimes call it En, or anyway. So you all know. So numbering operator is just like this, acts like this. Okay, and then in Schrödinger picture, in Schrödinger, I mean, a bit boring maybe for you guys. Picture. In Schrödinger picture, the state will evolves as time by unitary transformation. T0. So U T0 is e to the I h t minus T0. Okay. Minus sign. So therefore, I mean, it's about showing the picture. The state will change as the in unitary transformation. Okay? Therefore, you get the Schrödinger equation. Oops, sorry. So you get the Schrödinger equation like this way. In terms of this harmonic oscillator, e.g. Harmonic oscillator, so the Schrödinger equation of n of t. So this state will evolve as time goes by. So therefore, numbering operator, it satisfies the following equation. It should satisfy the following equation for excited states at the lower end. So this is the familiar story. It's a bit for I think I bored you. Heisenberg picture. Instead, we fix the state, and then the operator will change as time goes by. So therefore, we fix the state, so there is no change in the state in Heisenberg picture, but the operator h of t is equal to then you just use the unitary transformation operator of Schrödinger of unitary like this. So it's very familiar story, and then you get the Heisenberg instead of Schrödinger equation. I mean, Heisenberg equation is already introduced last time from the classical mechanics. I for h of t so this is the Heisenberg equation. In the case of a harmonic oscillator, So we just have the EDT of AT is equal to computational ratio AT and H. And if you use this computational ratio, you get the plus omega T. And then also what you get, So, and if you apply, so this annihilation operator, annihilation creation operator is the opposite sign in the same dagger of T. This is the creation operator, and this is minus omega dagger of T. And from here, what you get is AT. Dagger T is the change in the sometime T. Okay, I call it T0, and then E to be minus omega T minus T0, dagger T0. I mean, it's boring stuff. You already know. Like this. And this plays a very important role in canonical quantization free scale. So that's why I review by the crash course, lightning review of the harmonic oscillator. And you guys should know. Okay. So here we start with Hamiltonian, and we impose the canonical computational relation, and then we look at the spectrum and so on. So we will do the very similar thing for free scale. Any question at this moment? It's too easy for you, I think. Okay. So free scalar, we quantize this Lagrangian. To do that, we introduce last time we already introduced the conjugate momentum. And this is the essential phi dot. So remember phi dot of Tx, whatever. Okay, and then now, so we will do very similar thing. So we have a coordinate and momentum. So in the free scalar theory, we just do apply the following computational relation: phi of x, and then pi of y. So now we are working. First, we're working on Schrödinger picture. So therefore, so we treat phi as an operator. Now we treat phi as an operator, like quantum mechanics. We treat coordinate as an operator, right? In quantum mechanics, we treat phi as an operator, and if we use the Schrödinger picture, it's independent of time. The operator is independent of time. Okay? So therefore, we can impose the canonical quantization as the following. So now, here coordinate and coordinate and momentum the operator, and you introduce canonical. So we will do the same thing. So phi corresponds to Q over there, and pi corresponds to P there. Okay? And then canonical computational ratio is I, as over there. But now here the field, since it's a field theory, so it depends on the space-time coordinate. Therefore, we just impose the following dot function. And the other is 0. Other computational relation, other commute. So, which means that I will often use this notation because what's important is this one, and then what's left is phi always commute, whatever you call it. And pi also is also commute. Okay? So that's what I meant by other commute. Okay. And then essentially canonical quantization essentially do the impose this relation, treat phi and pi as an operator, and impose this relation. That's it. It's super easy. And then we will see the consequence. To see the consequence, we do the Fourier transformation of this field. So we do the Fourier transformation of phi. Okay. So this is a normalization appropriate. I will explain why this normalization is good later. But anyway, so this is a normalization for Fourier transformation. You should take a look at the notation of Pascal-Schroeder. And the pi of x is just a time derivative of this guy. So therefore, this is equal to qp 2 pi cube minus I square root et over 2 AP e to the I p dot x minus a dagger e to the I p dot x. So this is the Fourier transformation of the phi since it's time derivative. I mean, so later I will introduce the same thing. So this part is the same as so the cube. I will explain later why this should be the case. Cube is square root 2 EP square root. It's essentially the same as the e to e. I will explain later. This one is essentially the same as e to the I p dot x, and then you just impose p squared is equal to m squared. Essentially, I will explain why this should be the same. So therefore, if you apply the time derivative of phi, essentially the p0, you just get the from this time you get the IP0. So therefore IP0 is essentially I think essentially equal to minus IE P. Okay. So you have to be careful about the sorry, I think so I need to be I'm not to be careful about the sign. But essentially, what you get is the if you take a time derivative, you get the I times EP. So therefore, this cancel EP cancel. So therefore, the denominator becomes numerator EP, and then you get the extra sign. And the relative sign is the difference between plus and minus. Okay. And this is the consequence of Fourier transformation of the phi and pi. Okay. So let's first accept this Fourier transformation. I will explain a bit more detail about this Fourier expansion later. So let's accept this Fourier transformation, and what we will see the consequence of canonical quantization. Okay. So canonical quantization, if we just impose the phi and pi, we treat phi and pi as the operator. So therefore, so this mode is also becomes operator as we saw. So as we saw in harmonic oscillator, so these are operator. Now, I shouldn't use the yellow. So these are operator now. So therefore, Fourier modes are also operators. Oh, sorry, I think I should P here. So each momentum, I would, these are operators. So therefore, so we would like to know the commutation ratio as we saw in the harmonic oscillator. What are the commutation ratio and a dagger? So to see that the, so we just need to know a P, a Q, dagger. So we would like to understand the commutation ratio like this. We will do the same thing. What is this one? And recall that the, so this is this Fourier modes of phi and pi. Okay. So therefore, we just, to get this one, you need to do the inverse Fourier transformation. Okay. So therefore, AP is just dqx. So to get this one, you just need to mark appropriate factor and cancel each other, cancel this a dagger to get this one. So therefore, to do that, the EP over 2 square root of phi of x I EP pi of x. So if you multiply this factor, you get the correct factor and then they cancel. If you add them up, the a dagger part cancel. Okay, and then you get the inverse Fourier transform. You can extract AP. And the same thing happening here. AP dagger is equal to dqx. Oh, sorry, e to d. Sorry. So phi of x minus so of course the EP is equal to square root of p square and square. Let's we impose the equation motion here. So this is the A and A dagger. And we just need to look at the canonical quantization of this guy. And that's super easy. So again, as we saw last time, so the cross term is only important. Okay? Cross term is important. So the same thing happening here. Cross term is important. So what we have is dqx, dqy. You need to use a different coordinate, dummy coordinate, and then e to the minus ipx plus q of y. And then minus I over 2 EP and EQ. And the first one is phi of x and pi of y. So that's a cross term like this way. And now I just change x to y in bottom and p to q. Okay? P to q. Because I mean we want to use q for qq. Okay? And the same thing, the other cross term is indeed equal to I over 2 EQ and EP, and then pi x, alright, there's no space unfortunately, y, and like this way. So that's the other cross term. And now we impose this, what was it? The canonical commutation relation over there. And this is equal to anyway, e to the And then what we have is 1/2 squared EP EQ plus squared EQ EP and delta function. Sorry, x and y. So that's what we have. So this part stay as it is, and then we just impose this canonical extension. Essentially, I count down with this I, and then you introduce the delta function, and you have to be careful about this sign. That's it. Okay. And then I will continue. And what we need to do is just perform the integral. I think from the back it's hard to see. This is a bit more eye-friendly. And this one is equal to okay. And this one is equal to you just perform the y integral so that the 1/2 square root EP and EQ plus square root EQ EP, which is you can bring out of the integral, you just perform y integral. And then y becomes x due to delta function, and what you get is this one. E to the minus I, E minus Q, X. Okay? And then if you perform this one, it's super easy. You just get the delta function P equal to Q, and be careful about normalization. And the careful normalization will give you 2 pi Q, and P is equal to Q. So therefore, they count down the EP over EP. And then we have a 2 here and 1/2 count out, and what you get is delta function, just P plus Q. Okay, so therefore, if you do the inverse transformation, you can easily see that we have a desired, oh, I already erased, sorry. so in harmonic oscillator, we have a dagger is equal to 1, essentially. Okay? So we have a very similar computation relation for field theory. Instead, here there is no dependence on momentum in each mode. Okay? Here there is no dependence on momentum for harmonic oscillator, but here field theory, since phi and pi are depends on coordinate. Okay? So therefore, the Fourier mode should depend on momentum. And the Fourier mode we now treat as an operator, and the computational ratio is what we want. 2 pi cube delta function. And then it's a good exercise to do. Others commute. Which means that the AP, AQ is computational ratio. It's a good exercise. I'm not going to do that. So other commits me this. Okay. So the Pesky and Schroeder actually kind of cheated. They just so to get this Fourier analysis, they just do this kind of computation relation, I and Y. So, and plug this Fourier expansion into there, and impose this computational relation and a dagger, and then verify this computation relation. Yeah, do I understand what I mean? The Pesky and Schroeder, but that's not the right way to do. So the plug into this computation relation without deriving is a kind of cheating. So. Anyway, so everything works by imposing. So the the honest thing to do is just what I have done. So do the Fourier transformation to get to extract the n and dagger, and then just compute computation rate of n and dagger. The Peskin should do opposite way. So just plug this Fourier mode into here, and impose this computation relation, and to derive this canonical component. Anyway, that's what Peskin should do. And then so in the homework, I ask you to do the same thing for complex free scalar. So I ask you, so you have to do the Fourier transformation like this to derive the computation relation for creation and annihilation operator. So in complex, so it's the essentially complex field of X is can be understood as the phi of X plus phi 1 times I times phi 2 of X. So now here I treated phi as a real field, okay, real field. So therefore, n and dagger are just the complex conjugate each other as a Fourier mode. Therefore, it's a real mode. On the other hand, so if you use the complex field, so you get some creation operator A and A dagger here. Of course, it depends on P and Q. And from here, you get the B and the B dagger. P, Q, whatever. So there must be two Fourier modes should show up for complex scalar field. And you have to show the canonical quantization in the same number, in the homework. I hope you understand what I meant. If you don't understand it, you can just come to my to me at the office hour. Any question at this moment? Okay, now let me move on. In that case. Okay, I hope the recording is okay. So there's some foreigner is outside of China is taking my course. So recording is very important. The first 1 hour was missing last time. I hope it's okay. Okay. So now we would like to do the analysis of the again. What is the Hilbert space? What is the energy and so on? So that's what we did for harmonic oscillator. So to do that, we just do the following thing. I forgot that I wrote it. So this Hamiltonian in Q3, as I introduced last time. So this one is equal to 1/2 phi dot square plus this is what we derived last time. I will erase this part. Of course, this one is following the definition of the. I hope you already remember. That's a Hamiltonian definition of Hamiltonian, and this is Hamiltonian density, and this is Hamiltonian density. Okay, I hope this is okay. And then we just plug this Fourier transformation as an operator and plug that one into here. And we would like to, and we treat again Hamiltonian as an operator. Okay. So harmonic oscillator case, H is equal to omega A dagger A plus 1. And this is also operator, right? So we like to do the same thing for scalar theory. I just have written the result. So for instance, if you look at phi dot, I'm not going to derive everything, but phi dot is something like this one. So phi dot is equal to essentially this is the pi of x. Pi of x. So therefore, essentially this one is equal to this. Okay, let me write down honestly. So phi dot square is essentially pi square, and this is equal to. Okay, only this part I will write down honestly. EQ, Q, and then the rest you have to derive by yourself. Minus 1 square root EP over 2 square root EQ over P, Q, and AP, Q, E to the minus I. Sorry, maybe some of the students can get bored. It's just a direct calculation. So plug, you just do square root. But if you square it, you have to use the two momentum, P and Q, okay? And then just write down honestly. Plus A P dagger A Q E to the I E X minus I Q X minus A P A Q dagger E to the minus I P of X plus I Q dot X, and then there's another term. Unfortunately, you have to do this kind of computation to derive, but this is also horrible in this case. Okay. So this is the term for phi dot square, and we should do the same thing. That's delta phi, another phi square, and then it's very similar thing will happen. Let's see. Okay. So you just apply NATLAB into upper Fourier transformation, and what you end up with the same term, and this part becomes something like it's horrible. 2EP, 2EQ, and then what you get is minus P dot Q dot because of this NATLAB square. And then the same thing, same term as here, so this part, okay, this part is this part, and this part is this part, and so on. You have to do this kind of computation. Yeah. Sorry, I think it's time. Okay. It's yeah, and then do the same thing for this one, m square phi square, and then you have to do the same thing, and then plug that one into here. Okay, plug that one into here. So I'm not going to derive everything. I just give you the result. And if you plug that one into here, and you massage to the expression, what you end up with the following. So H. Anyway, so you have to do the honest computation and plug that one into here. And what you get is, if you massage it, what you get is what I'm doing here, e to the I P Q slash X, And then if you massage it, you get this one. Okay. Minus like this way. So you get this term. I think, I hope I'm not mistaken. Yeah, I think what I have written is correct so far. Okay. So this is the, if you massage this one, compute this one and the plug one in and massage a little bit, you get this expression. Now we just do the integral of the d cube x. So if you do the d cube x, what you end up with is essentially delta function. So okay, if you do the d cube x, it will give you delta function 3 and p and the q. Okay, with some number. I think 2 pi cube. I think 2 pi cube. If you are careful about the normalization, if you do the x depends on only c here, right? It's here. So therefore, you get the delta function. Okay. I hope you guys following it. And then you just do the integral q that essentially impose q is equal to p. Okay. I think I should go start plus. So that's why some people are skeptical. Some number. Okay. You have to be careful about normalization. I think 2 pi cube. And then this, if you do the q integral, that imposes p, q is equal to minus p. Okay. And then plug that into here, but you end up with the following. Maybe I should. But you end up with q e 2 pi or q dp okay. So that's what you end up with. Now, of course, I use the relation of the this relation on shell condition. EP is equal to this condition. Okay. If you use this one, you can do this. So just compare with Hamiltonian of the harmonic oscillator. It used to be something like this one, right? Like this way, right? And it's very similar. It's almost same. Essentially, you need to introduce momentum, and just need to integrate the momentum. Okay, that's why I reviewed the harmonic oscillator. Do you agree? Then what we need to do is bring this one into here. Okay? Then we know that the commutation ratio of A will give you this commutation and A will give you delta function. That we know. Okay? So now this is equal to d cube p pi or q that one. 1/2 0. In fact, 0. Do you agree? Do you understand? So hopefully you understand this the procedure. Essentially, this is equal to EP over AP plus 1/2 AP double. Okay, so therefore, just plug this computational relation of the n, and you get the delta function z. Okay. And we know this is divergent. This is divergent. So, but this term corresponds to this 0-point energy in harmonic oscillator. Okay, 1/2. So therefore, it doesn't. Even though this will give you infinity, it doesn't look like so harmful. Because here, since we have infinite many harmonic oscillator, this infinite many harmonic oscillator will give you 0-point energy. But this can be understood as the consequence of the. Where should I erase? Maybe I should erase. Consequence of that we are doing Fourier analysis in infinite, the space-time is infinity. So for instance, so volume of R3 can be understood as the d cube x, and this can be understood as the limit p goes to 0 of the d cube x e to the I p x. So rpx, so therefore this can be understood as a 2 pi cube delta function. So therefore this term can be understood as the volume of R3. So it's since we are doing analysis, Fourier analysis at the infinite space-time, so therefore this delta function can be understood as the consequence of the space-time is infinity. So therefore it's not harmful. So this 1/2 shift is not so harmful in quantum mechanics. Likewise, this one is not harmful to. So it's called infinite divergence, and then we can just simply drop. And then often people just write down that procedure. I'm going to erase here. Procedure coming from this term and dropping this term, what you end up with h. So usually just dropping this infinite term is called normal ordering. And then just put writing down like this way, 2 pi cube. Sorry. So normal ordering that you just put this thing called normal ordering. So the procedure is the bring creation operator. So in general, operator to the left, and then annihilation. Annihilation operator to right. So this is the operation. You just forget about the ordering and just do the bring the creation operator to the left, annihilation to the right, and simply forget about this constant. So that's it's called normal ordering. So that's kind of procedure we will do. So we will drop this term because this one you can be understood as the volume of the space-time. Any question? Is it okay? Let's do the same thing for P. do the same thing for P. So P moment output is just a, it's just a, and this is indeed equal to okay, so that's the thing. And we need to plug again this. Sorry, I already erased. I should have erased this one. So the Fourier mode I erased and plug that one into here, and what you get is as follows. Should I derive everything? Okay, let's derive everything for you. Sorry, it's maybe boring for you. Minus I square root E 2, and it's coming from pi, and then sorry, maybe for you a little bit boring. IQ. This one, nabla acts on phi, that's why you get this one. And then computational ratio will give you the following: AP, AQ, E3 minus I. Anyway, you guys should do it by yourself. Sorry, I maybe get you bored. If you don't like this kind of derivation, just tell me. If you don't like this kind of, maybe make you a bit boring. I don't know if I should do or shouldn't do. Anyway, you understand, right? Maybe I shouldn't do it. Anyway, so this is the expansion, just honest transformation, just plug it into here. And do the same thing. Again, just do the integral dx, you get the delta function of P and Q. You have to be careful sign. And then do the another integration Q. Okay? And what you end up with the following. And as you can easily imagine, so since this is just a integral momentum with the EP, and we just ignore the constant term. So therefore, if you do that, and then if you forget about the constant term of this again, if you impose normal ordering, so which means a drop the cube zero term. Drop the cube term, you just need to replace EP by P because of this one. Sorry. Okay, so that's what you get. This is big P and this is small p. Be careful. So in my lecture note, it's cleanly written, but in handwriting it's horrible. This big P and it's small p. Okay, so that's what we get from the. Okay, and then of course that the this is supernatural consequence. Okay, and now so we just look at the computational response H and P, and this is super. Just do the computational and diagram and so on, and what you get is this very, very natural consequence. Sorry. and then H. So you can get this kind of computation relation. I mean, so you just do the H a computation relation, and then whatever AQ and the A dagger will give you, if you do a computational relation, you get the delta function, and then perform delta function, you pick, sorry, not omega p, sorry, EP, sorry, I should use EP. I think I should change my lecture note. Omega p and the EP is the same. Sorry. So this is desired relation. We already looked at obtain this relation in harmonic oscillator. Harmonic oscillator, you just have the subscript p. So that in free scalar theory, we just have a vacuum which has an infinite many energy because of the infinite many volume, but we just drop. So therefore, we can understand as the energy is zero. So the vacuum is just the energy is zero. But this is ground state. And for excited states, we just apply the creation operator as harmonic oscillator. So but now we have the subscript p, so therefore we just need to apply AP1 dagger, AP2 dagger, and total AP and 2 vacuum. Okay. And however, so I'm going to explain why later. We need to multiply here in square root 2e1, 2e2, and so on. So I will explain why we need to normalize like this one later. So if you normalize this one, everything works perfectly. And the energy is of course equal to sum of E1 plus E2 plus plus En. So that's the Hilbert space of the free scale. So you just apply the ground state, the creation operator with momentum, whatever pi, infinite many way, to get the Hilbert space of the free scalar, and this is called Fock space. It's just a creation, infinite many creation operator due to the field theory. It's super easy so far. So Hilbert space, this curly H is just Hilbert space. It's just a sum of P1, P2. So this is called Fock space. This Fock space. So you just apply infinite many way the creation operator and just sum over all the states. So that's a Hilbert spectrum. Any question at this moment? Yes.
You use the annihilation operator on the state. What will happen?
Or annihilation operator to this which state? Ground states.
No, the P1, P2.
So you just do the analysis. For instance, if you apply annihilation of P1 and the P1 dagger at 0, is essentially what you get is the delta function, right? 2 pi Q delta 0 plus AP dagger AP axon 0. Okay, I see what you mean. So that therefore, this one is 0. This one you need to be a bit careful about how you treat. This time you need to be careful about how you treat. But depending on the situation, I mean, Let's see. I mean, depending on the situation, how you treat this one, that's a good question. If you act on a P, is there the cost of that function? Most likely you need to, I mean here, it's a bit, let me think. I mean, the way I would act is, acts on this P state, then what you get is essentially what you get is the Q 2 pi of Q, and the A and A dagger will give you 2 pi. Anyway, I don't like this kind of normalization, but 2 pi cube nabla cube Q minus P. Okay, do you understand? Do you understand? And then if you perform the Q integral, what you get is just what you get is just a P 0. It's just 0. Just 1, right? Yeah, one state. I think just state the action just vacuum. Like this way? Like this way. That's how I act. If you depends on how you act. Act on the annihilation operator, then the situation will change. Okay. Anyway, let's take a break for 10 minutes. I try to find a better answer to this question. And then if you please do not walk here during the break. If you want to ask, please come here, or if you want to walk, please walk here. Yes.
I want to know what's the range of the integral of Q? Yeah.
From everywhere.
So from negative
Minus
infinity. So what's the if Q is negative, then does that mean that AQ is a negative Q dagger?
What I mean? So Q this can make a negative one.
If you take the whole Q2, so if you add a negative sign,
Yeah, it's totally fine.
yeah, so is that the number? I mean, is a negative Q and a Q dagger, are they the same?
No, it's not the same.
But they act on one state and they will give the.
So this will give you, if you ask A minus Q dagger, so then that will give you the state which has a momentum Q is equal to something like a minus Q1, minus Q2, minus Q3. That will create the state which has momentum like this. But A minus Q is just annihilate the state that has the momentum. AQ, essentially as a Fourier mode, AQ dagger is just, as a Fourier mode, it's just a complex. As a Fourier analysis. But now we treat it as an operator. So this becomes creation operator. It's not a natural like a star, but as a Fourier transformation, it's just star. If you treat it like a classical number is just a star. But it's not operator, so I treat it like, I wouldn't say star. But that is not related to minus Q. Minus Q is just a I mean, it's just that what you said is something like that. The x is here and minus x is here. Phi x, whatever, phi x is not the same as like a phi star x. It's not the same. The same thing. What you're asking is
What's the future add the term to make the should be symmetry? What motivation that has to be that?
The energy moment needs to be symmetric. Yeah, I mean, I told you, so the thing in here, the intrinsic dimension should be like this. This is really intrinsic dimension. But to try the approach from this theory, you need to add something. That's what I try to do.
We need to add a
Many jobs. It's not unique. There's also a way to choose to make it this way.
number of 也要积分，就是你要对所有的题做积分，然后才得到一个正确的。因为你单独里面随便拿出来一个黑题，它会坏掉。 这上面像这些方面，但其实为了方便
pretty small. Okay, shall we resume? Is it okay? Okay, so now, I'm going to explain why we need to modify this scar root to e to the states, and then I'll explain what a bit more Lorentz invariant way to formulate the canonical quantization. That's what I'm going to do. Okay. So what we did is that So we define the vacuum like this way. And then the reason why just put the square root EP is as follows. If you take an inner product, okay, if you take an inner product Q and P, then what we get is that essentially we have square root 2BQ, 2BP, and then 0, AQ, and then a P cover, and 0. And then, as I mentioned, this one is equal to 2 EP, 2 pi of Q. So like this way. And then the reason why I add this square root 2e is I want to get this 2e term here. Okay, 2e term here, and then the reason why is that so clearly I want this inner product to be inner product of Lorentz invariant. So it's just some scalar quantity. It's just a vector or bra and a cat, and just multiply inner product, and we want this quantity to be the Lorentz invariant. To see if it is Lorentz invariant, we need to see how this delta function behaves under Lorentz transformation. So now we consider Lorentz boost. In x1 direction. So x1 direction. So as I mentioned last time, I saw the gamma b. I forgot the minus gamma b. Sorry, gamma 0 0 0 0 0. Okay, 0 0 0. Is it minus or plus? I forgot. Which should be plus. Sorry. Thank you very much. It's plus. It should be plus. So that this kind of transformation we'll consider. So the delta Q P minus Q, which is the delta. So note that the delta function behaved under transformation. So delta f of x minus f of x0. So we will use this kind of property of delta function. Okay. Okay, and then if you use this kind of relation, so what we have is essentially prime and the Q prime, and then we have the corresponding cost of the Lorentz this time, which is essentially now dp1 prime dp1. Okay. So that's the, I just apply Lorentz transformation. Now I use as the p as a function of p prime, okay, p prime, and q as a function of q prime. So therefore the cost is just a derivative, 1 over derivative. And we know that this just plug that way to here, and this is indeed equal to delta cube of p prime and q prime and gamma plus 1 plus b dp plus dp1. Yeah, this is just a standard analysis of the this. So gamma. I already forgot how you. also not a plus. So gamma times. Gamma times this one. Then what you get is that this is equal to delta Q P prime times Q prime, and this is equal to gamma over E, and then E plus B P1. And then this is equal to you just apply the Lorentz times, times. And this is Lorentz transformation. When using Lorentz transformation, do you understand what I'm doing? It's equal to E prime. Times, What I'm doing here, E. Do you understand what I'm doing? Well, hopefully it's okay. So from here to here is very easy, right? So you just multiply E over E here, and DE over dP1 is P1 over E. Is it okay? And E prime is just E prime is just applied the Lorentz transformation, essentially gamma B, gamma 0, 0, 0. Anyway, 0, 0, 0, and you just apply E1, E and P1, and 0, 0, okay? Then you get the E prime, P1 prime, 0, 0, okay? Do you understand? Is it okay? Okay, so therefore, if you do the Lorentz transform delta function, the cost is E prime over E, okay? Cost is, so therefore, this quantity E over is it okay? So if you do you understand? If you don't understand, just tell me honestly. So I just apply P prime 1 is this guy. So then the derivative is this one. So okay, right? I hope you understand. Or if you don't understand, just tell me later after. Sorry, is it my fault? Anyway. So just multiply capital E here. This is the Lorentz invariant quantity. Okay, do you understand? So after Lorentz transformation, E times delta function will give you Lorentz invariant quantity. But therefore, we need this. I will explain why I multiply 2. But we need this E time to make it Lorentz invariant. Are you guys following? So this inner product of Q dot P should be in the I want it to be Lorentz invariant. In order to do that, you need to multiply E in front of delta 3. Therefore, you need to multiply square root E. Then I will explain why we need 2 here. Okay. Also, what we have is so if you do the Fourier analysis, so we always have this kind of term, right? Q pi Q 1 over 2 EP. So in the Fourier transformation of the Fourier transformation, we use this kind of quantity, and then we like to see that this one is indeed Lorentz invariant. So this way you can just massage into the following way. To the fourth 2 pi 2 EP, and this is equal. 2 pi 2 pi delta I just want to use this kind of, sorry, this is Sanger. Okay, to go from here to here, I use this one. Okay. And this theta function is a heavy-sided step function. Theta of x is just a, okay, I think I should write down like this. It's much easier to understand. Theta of x and x is just like this way. So if x is supposed to be just 1, x is negative, it's just 0. Okay? So which means the P0 is only positive you will see this integral makes sense. Okay? So therefore, they pick only this term. P0 should be equal to EP. Okay? And if you use this one, let's see. Yeah, if you use this property, this is P0 square minus EP square, right? EP square, okay? Essentially, you can use fx as the x square, okay? The derivative of x square is 2x, right? 1 over 2, you have a 1 over 2x, and then just plug x or P0 equal to EP, and you get this one. Okay? Do you understand? Hopefully, do you understand? So this is 1 over, here, 1 over 2x, and x is equal to EP. And we only look at the P0 is equal to positive. If you don't use this one, there's a minus EP, there's a choice minus EP. So therefore, you may get the minus sign here. But since we impose P0 to positive, we only see this one. Okay? Okay. Therefore, this is equal to dq force 2 pi. Okay. So, as you can easily see, this one is manifestly Lorentz invariant. Lorentz invariant manifestly. Okay. And this one is manifestly Lorentz invariant because p squared. So now, I don't write like this vector. So it's a full vector. P squared is just a. This is what I meant. Okay. So the manifestly Lorentz invariant this guy. That function. I think I should say yes. That function. And the theta p 0. Is also Lorentz invariant because under the Lorentz transformation, the sign of P0. So if you have a light cone, so under the Lorentz transformation, the sign of the P0 does not change. Okay, this direction does not go to this direction. Right? So this light cone does not flip to this past light cone. Future light cone does not move to the past light cone under the proper Lorentz transformation. So therefore, this one is also Lorentz invariant. Okay? Sign doesn't change, or P0. Therefore, this is manifestly Lorentz invariant quantity. Okay? So this 1 over 2 EP is the multiplication is very important. Okay. So motivated from this analysis. We introduce the following quantity. Okay. Okay. So we will see why I multiply square root here. So so you can easily see there are 2 EP appear here. So therefore, I multiply with 2 EP, and we will see much more clear. It's much more clear in the following reason. So now, so we introduce the identity operator. In momentum space, I mean, on the one particle, human space, which is identity operator. I mean, in quantum mechanics, you often just multiply this kind of term, right? All the state. I the all state, this is the identity operator. You introduce this kind of operator. It's the same thing. And we wanted identity operator also Lorentz invariant. We just use the Lorentz invariant measure. 1/2 EP. So that's the case, and then if you want to, okay, and it just acts X. So the position operator. So we want to define the canonical conjugate or like a Fourier transformation of this guy. We want to define the Fourier transformation of this state. Then what you have is this one. And by definition, this guy is e to the I minus IP. Therefore, okay. So I just define as this. I mean, this is usual quantum mechanics. This is equal to e to the minus I. I think red is hard to see from back. I think I should use the yellow. And then I drop yellow somewhere. Oh yeah, here it is. And this is equal to E3 minus I P dot X. Okay. So this is the Fourier transformation of the states in momentum space to the coordinate states. Okay. Okay. Then we can do the same. I mean, and if you do this one, you can easily guess, right? It's just conjugate of this conjugate Fourier transform. So this is complex conjugate. So then, I think. I mean, it's too boring for you guys, I think. And this is equal to e to e, which is complex conjugate of this one. Okay. Okay. That's the rule. And then we want to be a bit more careful about this state of X. And this can be understood as follows: dqp. You can just write down. So now you understand why I put this 2 over there. Square root 2e. Vacuum, and this is phi of x, x on 0. Do you understand? So now we know, so just try to compare this line and this line. And to create the P state, we need to multiply square root EP a dagger, right? A dagger. So therefore, so we just apply this one into here. And 1 over 2 EP cancel square root 2 EP to get 1 over square root 2 EP. Okay? And then, so this is a term which comes from here, and we simply just add this term because it just annihilates. And this is the Fourier expansion of the operator phi of x. Okay? We saw before. Okay? So therefore, if you add this operator phi of x, it creates the states of x, which is Fourier conjugate of this P. Do you understand? Do you understand? So phi of x, from phi of x, this is operator, and if you do the Fourier transformation, you get the AP, right? AP dagger or phi of AP dagger. If you start with phi of x and the Fourier transformation, you get the AP and the AP dagger. Okay. From here, so there is Fourier transformation. From here, you can create the state, one particle state in momentum space. Okay. If you do the Fourier transformation from momentum space, you get the state in the coordinate. That can be created by acting on phi of x on vacuum. And therefore, they are Fourier conjugate, Fourier, how to say it? Dual to each other. Do you understand? This x and the reason why I put the square root 2 EP is to get this 1 over square root 2 EP. Hopefully it's understandable. Okay. So therefore, this can be understood as the one particle state in coordinate space. And this is one particle state in momentum space. Okay. And they are Fourier dual to each other. Anyway, so if you don't understand, just ask me at the office hour, or after the lecture. It's getting slightly difficult, but still, I hope it's understandable. My lecture is okay. So then, so this one does not look like manifestly Lorentz invariant, but we will make it a manifestly Lorentz invariant. And why I will explain why the Fourier transformation pi should be take the one I showed. To do that, you will see the condensation in a Heisenberg picture. Okay. So now, so I treat phi of x as the operator in Schrödinger picture. Now to make it the Heisenberg picture, we just have the following. I mean, you know. And then we do the same thing for harmonic oscillator. So that's why I review harmonic oscillator. E to the I, HT. And if you use the Heisenberg equation, we know, I mean, it's natural cos sequence to have this one. I mean, I think we. Yeah, so this is the case. Is it okay? So now I treat phi can change in the unitary transformation as the time goes by, time goes on. So they're just sandwiched by unitary operator, and so therefore the Fourier mode are operator also, and you sandwich by unitary transformation, time transformation, and you get this one. Do you agree with that? And then plug that one in too. Okay. So then plug that one into the Fourier transformation. Okay. Sorry, no, sorry. There is no vector anymore. So this is the exactly. So now the AP has a time dependence. And this time dependence just instead of the inner product in space slice, this is now space-time inner product. So this part is just this one is P dot X is just a P mu and then X mu. Okay. And so this is indeed equal to P0 X0 minus P dot X. Okay? P dot X. So therefore this minus cancel, and the plus sign, and to bring back to the original formula. And then this minus I P0 X0 will give you this minus I EPT, right? Okay? The same thing you need to do here. So here becomes minus I P vector X vector, and this dependence of time is just this dependence of time I EPT is coming here, just imposing this condition. Sorry. Okay, and then we know okay. So now we're coming back to this pi of x and pi x and t, and this is just right. And then so this is I just give you the answer. Minus I third to EP. Are you no? So now, so the sign is clear, minus sign is clear, because here is a minus I here, and if you take a time derivative, minus I will show up here. Sorry, there's a minus sign here. Minus I appear here, okay? And if you do the time derivative, EP will show up in here, EP will show up in here, and becomes, so from denominator to numerator, okay? Numerator. And the relative sign comes from, here is the minus sign here, but here is plus sign. Okay? So therefore relative sign will show up if you take a time derivative. Do you agree? Do you agree? And then you just impose E0, P0 equal to EP. I hope it's understandable. Okay. Okay. If you have a question, just tell me. And if you impose from Heisenberg to Schrödinger picture back by just getting rid of time derivative, so that's exactly what we saw before, right? At the beginning of lecture. Okay? Hopefully it's okay. And then we can just do the canonical quantization as now in Heisenberg picture. So we just impose equal time. So this is the canonical quantization of Heisenberg picture. You have to impose equal time at each space slice. You have to impose this kind of condition. And also, other commute is also has to be equal time. Anyway, so this one is okay, to be honest. This one, it doesn't matter, to be honest. Anyway, it doesn't matter. Other commute is okay. Anyway. Okay, so this is the canonical computational relation. In either case, CCR is the canonical computational relation in Heisenberg picture. So needs to be equal time. So computational relation equal time. So in other words, you have to impose canonical quantization at the time, each time slice t, the time each spatial slice at the same time. At the same time. Any question to get the correct? So from here, one can derive AP bagger is equal to 2 pi cube delta cube. Sorry. So now we are going to talk about causality. So the causality So causality tells us the following. If two are separate by spatially, space-like separation, the measurement here does not affect the measurement here. Okay. So that's the causality. Causality means if point X, point Y are separate as space-like, the measurement here does not affect the measurement here. Okay. So in other words, operator OX has to commute if X, Y are related by space-like. So this is space-like space separation. Separation. So this guarantees so this means that if you just so even if first you measure O1 at the point X and then measure O2 at space-time point Y is equal to you measure first O2 at space point Y, and then you just measurement is just essentially whatever physical state and physical state essentially just like this. So this should be any physical state, any physical state, the sandwich them in always Z. So this means that if you first measure O1 at point X, the next O2 point Y is the same as you just measure first O2 Y at the O2 point at Y and the O1 point X. Okay. So therefore, if they commute, the measurement point at X and Y does not affect the order. The order does not affect. So to check that this so we just want to compute the computation ratio of phi x and phi y. And just what was it? That one just plug into here. Again, I need to write. Oh goodness. Okay, so just plug that Fourier analysis, Fourier transformation to here, and just impose computation ratio of this one, and plug that one into here and do the integral. And what you end up with as follows. Yeah. Okay, then, so as you can easily see, so what's relevant is cross term, this one, and this one, and this one, and this one. And then, what you end up with, if you do the integral of d cube, what you have delta function, essentially. Am I correct? I think delta function. Yeah, so delta function as sorry. So if you use my brain's not okay. AP and if you do AQ, you get the delta function, right? And if you do the integral of dq, you have to impose p equal to q. Okay? And that so therefore q will disappear. You just set the p equal to q to get the 1/2e. And then set the Q to be P, you get this term. And since the now computation, if you look at the computational relation here, the order is different. So therefore you get the minus sign. And you have to be careful of sign here. Okay. And I call and I define first piece as d x minus y. And the second piece is d y minus x. So I define the first piece, this guy. This guy is equal to dx. Then automatically, by definition, this integral will give you d y minus x, and the minus sign is just here. Any questions so far?
I have a question.
Yeah.
So as far as I know, that the field operator isn't such an observable function. But so why should our causality be like such?
The field operator is the operator, so it's observable. No, it's just an operator. So this is also operator. This is the operator.
Okay.
Yeah. The observable operator. So we define the state x as just this phi axon 0, right? This is the one particle state in the coordinate space.
But actually, it doesn't yield any experimental results just with these phi fields. I mean, okay, maybe I should re-express my question later.
Okay. It's an operator, and it's this operator. This vacuum can act, right? So therefore, it's definitely observable. Vacuum. This operator can act on vacuum, so therefore, it's definitely observable. And what I'm doing here, so I just define just compute the commutator of phi x and phi y, and then so we want to see that they obey the causality. So what we want is that the so what we want is that the so what we want to show is if 0 if for like this. That's what we want to show. So that's very easy to know because if x and y, so this, as I mentioned, this is Lorentz invariant quantity. So this quantity is Lorentz invariant. Okay. So this is, as I mentioned, this measure, integration measure is okay. So I think it's right. This measure is Lorentz invariant, and this inner product is Lorentz invariant. So this quantity is Lorentz invariant. Okay. The same as here. This quantity is Lorentz invariant. So both are Lorentz invariant. So therefore, even if you do the Lorentz boost or spatial rotation or whatever, this quantity shouldn't change. Okay. And if there's x and y, if x and y are spatially separated, whatever, with light cone and then whatever spatial slice. Okay, so that's for simplicity. X are here, x is here, y is here, and it's just you can just rotate, right? To bring x and y to. Sorry. I shouldn't mention like this way. So x minus y is x minus y is this vector, okay? This vector, and y minus x is the, I should use the red chalk. This is y minus x, okay? And this yellow can bring to red by rotation. Okay, by rotation. So therefore, this quantity should be equal to this quantity if there's space-like separation. So therefore, this should be 0. Okay, this quantity is equal to this if there is space-like separation. So therefore, the causality is done. Causality is checked. But however, so I'm not going to derive. So each quantity, so this. So this is indeed, if you compute this one, if you compute the correlation function, 2-point correlation function, I mean, do the same analysis. I mean, essentially what you get is the, instead of commutator, you have just a phi x, phi y, and it's just sandwiched by vacuum. Sandwiched by vacuum, and what you end up with is this quantity. Yeah, as you can easily see. So first you need to act a dagger. Next you act a p. Then impose this canonical commutation relation, and you get that function, and you end up with this one. And this is indeed the same as the one I have written, drawn here. So this one here. So this is d of x minus 1 correlation function. And this is indeed this is indeed non-zero. So therefore, this, even if this is non-zero, so this is, you just look at the Peskin's derivation. I mean, I'm not going to derive Peskin's Schroeder. I forgot the page number, but anyway, even if spatial separation is 0. Even spatial separation, this is non-zero. But this is okay. Even correction function is non-vanishing even in spatial. That doesn't violate the causality. This doesn't mean that the one measurement at the point x affects the measurement on point y. Doesn't mean. So it's totally fine. So in fact, I mean, okay, let's use this. If you go back to long path, so let's use orange. Even though there's spatial separation, if you go back to long path, it's, I mean, some event here will affect this light cone, right? Therefore, this event somehow affects this point and this point. Okay. So therefore, if you go back to the long path, this event has to give you some correlation between this point and this point. So therefore, it's totally fine that this 2-point correlation function non-zero, even if the space-like separation. That doesn't mean that it violates the causality. So that's a key point of the causality. Yes.
We calculate the commutator of the belt operator, and we get the zero value only in the space-like condition. But what happens in why it can happen in time-like condition?
Time-like condition. If it is time-like, definitely this is non-zero.
In time-like condition, we can do a Lorentz transform too, and we can.
No, you cannot.
So what?
You cannot.
一个请一个双叶的那个双曲面跳到另外一个图上。
Yeah. So this part, it cannot be transformed to the past, right? by Lorentz transformation. So Lorentz transformation is like this way. X minus y is the future. Maybe if it is the future, x minus y is the future. Y minus x is the past, right? So you cannot bring future to past by proper Lorentz transformation. Do you understand? Okay. Still, I have a time. Oh, good. So now I can introduce final propagator. Do you think it's fast? Is it okay? So now we introduce so-called two-point function in time ordering. So this is the just two-point function without time ordering. So we consider a two-point function. Time ordering. Which means that the so this is time ordering, and often people just write down this one is equal to 0 time order. Did I write? Oh yeah.
Yes.
Like this way. This T means time ordering, and then okay, good. So I can introduce final propagator today. I'm just wondering if I can reach there. Now, so this can be, so you can use a step function, Hepsize step function to introduce this quantity. I already raised Hepsize. So this theta is Hepsize step function that we introduced just before. Theta x, this one, and this one. Sorry, my drawing is horrible, but anyway, you understand what it means. So therefore, this can be understood as the, so that we know this one is equal to that one, and therefore, oops. No. Sorry, I didn't check the recording. Okay, I think it's. Anyway, I will do my best. So this is the case. Here, I just plug this one into here, but here you have to swap y and x, so therefore I have a plus sign here. That's the only difference. Okay? And I just want to write this one in a bit more Lorentz invariant way. So this means that this means the so this means that this is in future. So this means positive frequency. Frequency e to the minus I p dot x t is positive. In time in forward time in forward, and this is negative frequency. Frequency e to the I p x in backward. In time. So that's what I meant. In the physical meaning is just here in time. It's just if you go to future, you have a positive frequency. Here, if you have a negative, sorry. If you go to the past, if you have a negative frequency, that's what I meant. And we can just massage this this expression and then make it a bit more Lorentz invariant way from now. In 10 minutes, let me do that now. I think I have 10 minutes so I can do that. Okay, so first let's look at this part. And then to make it a bit Lorentz invariant way, so we already know this one is Lorentz invariant, and we can make it something like a, so this one, we already know that this one is equal to, I already forgot the expression I need to, my memory is horrible, so delta p square minus m square theta p0, right? So we saw that this measure is Lorentz invariant because this can be bring it to this one. We will do the similar thing for this expression. Is it hard to see? I mean, anything. Anyway, so it's recorded. If the recording is successful, no need to take a picture. You can just look at the video. So to this end, again we add the P0 integral to make it Lorentz invariant way, manifestly. So to do that, so again, dP0 2pi. So you just notice that this integral, we just consider this kind of integral. E to the I and this can be understood as the dq p0 2 pi r1 p0 minus dp. Let's go I p. Sorry, I think I should p0 plus ep and e to the minus I p0 x0 minus y0. Okay. And we just need to, so since there's a pole, we need to be careful contour integral. Then I will pick the following pole. There's a two pole in the P0 prime, and there is 0 EP. There's a two pole minus EP and plus EP, and what we want is to bring this expression. If you do the contour integral, what we want is this kind of quantity, 1/2 EP. Okay. So now we need to pick the pole here, impulse P0 equal to EP, and if you plug that in here, you get 1 over 2 EP. Okay? And this, as you can easily see, so that what we want is we want to pick this ball, but not this ball. Okay? So therefore, we just pick the contour something like this way. Like this way. And then cross the contour in from the bottom. So in this way, so this P0 is so this big circle is the lower half plane, right? So therefore, imaginary part is minus I. Okay. So therefore, P0 has a minus I, imaginary part. Minus I times minus I is negative, right? So therefore, if the radius is big enough, this radius is big enough, if you take a big contour, so this part does not contribute, okay? Because minus e to the minus r, and r goes to infinity, which means just a 0, okay? So this part does not contribute. So therefore, what we have is minus infinity to infinity, and pick this ball, okay? But you have to be careful. Contour is this clockwise direction, okay? So therefore, you get the negative sign, okay? So you have to be careful about it. If you do this careful analysis of sign, you get this one. 1 over EP, e to e, minus I, EP, x0, minus y0. This is exactly what we want from here, in here, okay? You understand? So you have to be careful. So that you have to do this kind of analysis. You learn it in the complex analysis, right? Z minus Z0, what was that? Ft is equal to Fz0. If you contour Z0 in anti-clockwise, okay? So, but you have to be careful of sign because of this. The order is different. Now next we focus on this one. We do the same thing. But here, so again, so the sign is minus I to EP x0 minus y0. But here it's a positive, plus I EP times x minus. So therefore, what we want is the following. I think you should do the same integral. But however, now what we want is to pick this ball, minus EP, and not this positive ball. And then, oh my goodness, I'm so stupid. So what we want is like this kind of integral. Oh, I'm very sorry. I'm so stupid. This kind of, and then now we consider the following integral. So now I just changed it to just order x0 and y0. Okay. Okay, and then we do the same manipulation. Okay, so now okay, let me continue. So that now P0 is upper half plane, so therefore imaginary part is the I, plus I. And then why am I doing this one? Plus I, oh okay, plus I, and but we mean, well, pick this ball, minus EP, so therefore minus I times I times minus EP. So therefore imaginary part is minus EPR or something like that. So if R is big enough, you have there's no contribution from big circle. Okay? And then what's left is this one. Okay? So therefore, and if you do the contour integral for this is C2, I call it C2 and C1. So this is C1. And this is equal to 1/2 EP. Okay. So therefore, if you combine, plug this expression into that one, and plug this one equation in the former one, what we end up with the following quantity. This is called this x minus y is the so, and the contour is just right C is taken. Unfortunately, time is almost over. Yeah, if I don't make a mistake, I just a bit more. C can be something like this one. Minus EP and EP. And then contour C is something like this one. Okay. Or sometimes so there is so-called epsilon prescription. So this can be written as the d4 to pi to the 4th p squared minus n squared I epsilon over I e3 minus ip x minus y. So this plus epsilon means that you just push this pole into a little bit. So this one, this plus epsilon prescription is that this one is just moved to, the pole is moved to somewhere around here. Pole is moved to something like this one. So minus EP plus I epsilon, maybe square root, I don't know, square root, and this is EP minus I epsilon. Epsilon, this epsilon, that epsilon is slightly different, maybe square root, half, or anyway. And it times over, and then we can just set the contour like as it is. Okay, and this is called final property. Of skeleton theory. Okay, let's stop here. If you have a question, just tell me.